Welcome back to the second half of the lecture related to Nernst and Rest potentials of software assignment 0. So we'll start on slide 15. So please get your slide 15 ready. In the previous lecture, we talked about the potential across a cell membrane being a battery. We also talked about how a battery needs a resistance or a load through which it can pass a current and do useful work. You can visualize how to light a bulb using the power outlet in the wall. Maybe you can sketch a schematic of that too. The battery, which is the power outlet, and the bulb, which is a pure resistance. The cell membrane in this case is a funny battery. The cell potential itself, like we discussed, is a battery, and it has resistors embedded in it. That is, the load is embedded in the battery itself and not outside, as in the case of the light bulb. Can you sketch a light bulb connected to a battery with plus-minus leads? Then sketch a cell membrane with a potential difference and insert a channel resistor in it and see if you can understand the equivalence. So pause this video, take a minute, and sketch a light bulb. Sketch an outlet as a battery. Battery has one long side, a line with one long side and a line with a short one. Just as shown in this picture here, which I can show you with a mouse, and then this resistance, which is actually the light bulb, and you can just connect these two back. So that's a schematic of a light bulb being charged by a battery, right? Now plot a cell membrane like you've done earlier in the class with plus minus charges on, and then convince yourself that's a battery. Now embed a protein pore in it, kind of like here, like they've embedded protein pore. And then make sure you write the extracellular side and cytoplasmic side. And then look at the equivalence of both and try to convince yourself they are the same thing. How this is itself, the cell membrane with these concentration gradient, is a battery. There are three panels on the slide 15. The one on the left shows a zoomed view of a membrane with one pore, which has a resistance. So before you get to this, before we start, make sure you've sketched the light bulb and sketched the membrane, as I said. Only then continue with this video. So I would suggest pause here, finish those sketches, and then continue with this video. So when you're ready to continue, I'll start again. This slide has three panels. The one on the left here, one in the middle, and one on the right. The one on the left shows a zoomed view of a membrane with one pore, which has a resistance. With ionic species inside and outside, there is no Nernst potential because there is no ionic species present here on inside or outside. Right? With no ionic species present, there is no Nernst potential here. There is no flow opposing any voltage. So you have a very simple Ohm's law here, which is V is equal to R times RK, or I is equal to gamma K. They use gamma here. I is equal to gamma K times V, which is exactly the same Ohm's law, but written in a different form. I is equal to gamma K multiplied by V. That is the format used by biologists. Engineers use V is equal to IR format, but biologists use I is equal to gamma or G conductance times voltage. In the middle panel, you do have ions inside and outside. That's a difference from this panel. You do have ions outside and inside. And so there is an existing potential difference that any voltage has to overcome. Right? So if you add a voltage, that has to first overcome the existing potential difference. So the Ohm's law for this case will be I is equal to gamma k times V minus Ek. Again, can you write it out, please? I is equal to gamma k, gamma subscript k, times V minus Ek in parentheses, where V is the voltage and Ek is the reversal potential for that ion. And that's what they're showing here. If you plot that, you will get a plot like this, which is essentially this curve shifted to the left. On the intercept on this voltage axis will be Ek. So the equation will be something like this. I is equal to Gk or gamma k times V minus Ek. Okay. So again, if you have, in reality, there will be lots of pores that we are coming to panel 3 now. In reality, there will be a lot of the same pores. So the equivalent Gk will be Nk. Let's assume there are capital N subscript k pores, Nk pores of type K, and each with conductance gamma k. So the total conductance here for all of these pores summed together will be Gk is equal to Nk multiplied by individual conductance gamma k. So the equivalent conductance for all these together will be Gk, and the reversal potential is Ek. So the total conductance Gk is represented by unitary conductance gamma k of a single channel and the number of open channels. So if you think about this, finally what you get is for any channel type, we have I ion is equal to G ion times V minus E ion. We sometimes use Vm, which M stands for membrane, and sometimes we just use V. So be aware of that. So the Ohm's law for this is I ion is equal to G ion times Vm membrane potential minus E ion. Or the current is equal to conductance times the driving force. We call this the driving force also. Again, pause a minute to make sure you understand everything well here in the slide. When you're ready, we'll move on to slide 16. Just when you're ready, get out of the pause mode and we'll continue with slide 16. Okay. So move on to slide 16. We ask the question, what is an equation for the membrane potential when there are multiple ion species? In the previous slide, we looked at I ion is equal to G ion times V minus I ion. Now the question is, what happens to the membrane potential when there are multiple ionic species? That's what we will try to look at in this slide and in later slides. That's a question we want to answer. Recall from the previous slide, we considered one type of pore only and came up with an electrical schematic with a resistance and a battery to model it. If we have 3 ionic species, we will have 3 such resistor plus battery schematics to model it. So you have lots of sodium pores. All together, they are modeled this way, GNA with a battery, ENA. All the potassium pores together are modeled with GK, battery EK, reversal EK, where GK is, remember, we had in the previous slide, NK times gamma K, and then the same for chloride. So if you look at this, can you visualize ionic flows? That's what we have to get to. But how do you put this together first? Remember that all of these are at the same potential, all of these are the same potential. This is extracellular side, this is intracellular side. So this schematic is how you put it together. This is extracellular side, all of these are the same potential. And this is intracellular side called cytoplasmic side, again the same potential. So you draw a line, connect all of this, then you probably get your first electrical schematic here in this course, where it's a combined model for three conductances, the flow of ions through a membrane which has three separate conductances. Okay. Again, pause the slide to make sure you understand everything here. And when you're ready, move on to the next slide. And as you pause, keep thinking of this. Can you visualize ionic flows? Right? What will INA plus IK plus ICL be at V-rest? So we will end the slide with this question. Write down your answer. And we will give you the answer in class if you don't get to it yourself. Again, pause the slide and make sure you understand everything before you move on to the next one. When you're ready, get to the next, we'll go to the next slide. So if you're ready to come to slide 17, we ask this question, what maintains these concentration gradients? If you go to the previous slide, you notice some slides before, there are concentrations inside and outside, right? What maintains these concentration gradients from changing? When there is flow of ions down a concentration gradient, you would think, oh yeah, maybe the concentration gradient has changed because some ions flowed out or in, right? So what happens is you have something called the sodium-potassium pump, which we talked about in class, which they work behind the scenes. They work at a very slow pace, but they keep maintaining the concentration gradients. As I mentioned in class, these pumps, here we show the sodium-potassium pumps, but there are calcium pumps. There are all sorts of pumps maintaining concentration gradients. They consume a lot of energy. For every burger you eat, 30% of that burger, energy in the burger, goes to maintaining these pumps in your brain. That's a lot of energy, actually. So let's focus on the sodium-potassium pump. This particular pump prevents dissipation of ionic gradients, right, for the sodium and potassium ions. That's what sodium-potassium pump's done. What it does is it takes 3 sodium ions are pumped out for every 2 potassium ions taken in. So think about concentration gradients. In your brain, the neurons, there is a larger concentration of sodium outside and a lower concentration inside. While for potassium, there is a larger concentration inside and a lower concentration outside. And these pumps actually maintain those gradients. Okay. When you're ready, we'll move on to slide 18 now. So this is a busy slide. To the schematic you had earlier, we will now add cell membrane and pumps, right, to the previous schematic. So this is the schematic you had previously. You had sodium, you had chloride, you had potassium. We know about this. Remember, the extracellular side is at the same potential, right? So you carry this forward. Now you're adding pumps. These are pumps. These two represent sodium-potassium pumps. Sodium-potassium pump, what does it do? It brings potassium ions inside. That's a current, right? If you bring ions in it, that's a current. And it throws sodium ions out, okay? And then we have our cell membrane, which is a capacitor. So again, this is a busy slide. We started with this section here, and then we are adding this. So I'd like you to, again, look at this slide very, very carefully. Understand it before we move forward. Some notes. Note that resistors here are all constant. They do not change with voltage. They model a passive membrane. These resistors lumped together are termed leak. All resistors that are open at rest can be summed together and called the leak conductance. So these are always open. And we have an equivalent leak reversal, which will be an equivalent of all of these leaks. Okay. And the way to calculate it, leak reversal, there is an equation at the bottom here. We will get to all of this math for this later, but I just want you to understand the concept here. And the equivalent resistance, you can sum this way. They can be summed and with an equivalent leak here. So again, we will come to this math later, but just understand the concept. How is this schematic put together? Okay. And then I'd like you to think, look at all of the other stuff in the slide. It should all be obvious to you. Again, this is a busy slide. Pause it, and when you're ready, we'll go to the next one, continue with the next. Now we come to this concept of resting membrane potential. We have all the tools to address that. Resting membrane potential is the V membrane, VM or V, without any input. There's no input coming into the cell, current or anything. It's just resting. And that's termed V rest, which is typically a constant for a cell, for a particular cell, and it may differ for different cells. And V rest typically is E leak or very close to E leak, implying that at rest only leak conductance is active. If that is true, then V rest is equal to E leak. What is the value of E leak typically? If you notice from the previous math, this has to be between ENA and EK. ENA typically reverse the Nernst potential of sodium is 55 millivolts, and the Nernst potential for potassium is close to minus 80 or minus 90 millivolts. So if you have a cell with only sodium and potassium ions, the rest potential will be minus 65, roughly minus 65, in that range. It depends again on the concentrations. If you look at typical concentrations in neurons in our brain, it'll be close to this, minus 65 millivolts. So that means some sodium pores are open at rest, but most open are potassium pores. And so resting membrane potential is typically less than K+. Okay? Less negative than K+. Okay, let's move on to slide 20. Now we are beginning, we'll start summarizing. The question is, what is rest potential? And we'll do that experiment we did in class. You buy the semi-permeable membrane, which is permeable to all of these ions. Now you need to find out the reversal potential when all of these are active. Please write down how you would do it on the right side. Pause the slide and make sure you complete this. Basically, this is a summary of what we've been talking about in previous slide. Again, move on to the next slide only after you're done writing everything asked for on this slide. So using first principles, the logic we use when studying mechanisms, write down the mechanisms involved in bringing the system below to an equilibrium. Bring it up in class if you have questions. Okay, pause, complete, and then we'll move on to slide 21. Slide 21 is again a summary. The resting membrane potential is the membrane voltage of cell in unstimulated state, meaning there is no input. Resting membrane potential of most cells is between minus 65 and minus 85 millivolts. Obviously, resting membrane potential depends on the concentration of ions inside and outside and on the permeability of each ion. Fraction of pores open. It is affected most by K+ because it is most permeable at typical rest potentials. How do we get an equation for V rest? The diffusion electrostatic forces are still at play, but separately for all the ions. We will not derive this equation, but just provide it to you. And you have to remember this equation. Here is the equation, V rest. This looks almost Nernst-like. RT by F, if you remember, is the Nernst, all there in the Nernst. There is no Z here, which is the valence of the ion. It's replaced. It's inside. It's sort of pulled inside in a sense. So this is natural logarithm. And pK stands for permeability of potassium in this case, multiplied by concentration of potassium out. Permeability of potassium multiplied by concentration inside. And so you take the permeability multiplied with concentrations, and that's a numerator. Outside for potassium, outside for sodium, but inside for chloride. This is the trick. You need to note this. This is because the valence of the chloride ion is -1. The Z here is -1. So it'll get flipped. Out will come down here and in goes up. So this is something you have to remember. Again, try to understand this completely. Let's skip slides 22, 23, 24, 25, 26, and come to 27. Slide 27 is a repeat of a slide from before, sodium potassium pumps. What it says here is the sodium potassium pump actually adds, the fact that it's there, it adds about -3 millivolt to the resting membrane potential. Just something for you to know, but not very important here, because we rarely model the sodium potassium pump in our circuits, as you'll notice. The reason being that the current due to this sodium potassium pump is very, very tiny. The important thing is the current continues constantly. Even when you're sleeping, that current is on. That's how they built up. But for a short duration, that current is so small you can neglect it. Right? It's kind of, if it rains entire day, but if it's a very, very light drizzle, that rain probably, if you consider any minute, really there's not much falling down, as opposed to heavy rain where there's a lot coming down quickly and it's all over. The sodium potassium pumps are like, I guess, very, very, very light rain. It goes on constantly, and they keep maintaining. As far as their significance as a current, it's a very, very small compared to the other current, so we'll typically end up neglecting it in later slides. Okay, but you should be aware it exists. So the resting membrane potential strongly depends on the external potassium concentration, as largely independent of the external sodium concentration. So if you plot concentration, this is a log scale in millimolar, and this is resting membrane potential. This is concentration of potassium. Notice that resting membrane potential depends strongly on potassium concentration. It changes. While for sodium concentration, it does not. For sodium, it does not change much. Okay, so that's because what you conclude from them as resting membrane potential is heavily dependent on potassium. Why? How do you quantify that? Well, why is resting membrane potential altered by changes in one ion but not the other? So that depends on the number and type of ion channels that are open at rest. It can be shown that at rest, mostly potassium ions are open. Sodium ions are not open at rest, typically. Can we quantify how the resting membrane potential depends on changes in ion concentration? Yes, we can. So that is done by the GHK equation, right? And that's where the permeabilities come in. Okay, this is again the same plot, but not on a log scale again. Because the permeability of potassium is 1 relative, and sodium is very, very small. Chloride is also very small. That is why I think potassium affects rest potential much, much more. So resting membrane potentials in real cells deviate from Nernst equation, particularly at low external potassium concentrations. Also, the Goldman-Hodgkin-Katz equation is a correct equation to use when you're multiple ionic species. Do not use Nernst equation in this case. Okay. Now these summary slides I will skip, but please go over them and make sure you understand them fully. Okay. I'll skip all of these summary slides, but you're supposed to go over them very carefully. Here's an example of the GHK equation for the squid axon. Go over that very carefully again. And if you substitute numbers, here's what you get. For the squid axon, we give you the concentrations on a previous slide, if you recall. It's very important you watch this resting membrane potential demo, because these things can come in the test. So these concepts are extremely important. Please watch it now that you have the background of what a resting membrane potential is. And then there are other websites which have very useful information. You're expected to go through all of this. All of this will appear on tests. At this point, what I'd like you to do is fill in the slides we just skipped. The origin of resting membrane potential, that's slide 22. Question we have is, if a cell rests, right? There are some potassium ions that have gone out to have this concentration gradient, right? If those ions leave from inside to outside, does it change the internal concentration? That's the question we have. How many ions have to move to maintain that concentration gradient for potassium in this case? So if the membrane potential of a cell is set in the first place by potassium ions moving down the concentration gradient, does this alter the internal potassium concentration? In other words, how many ions have to leave the cell in order to set up the equilibrium potential? So to do this, we go to math and you can calculate all this. Don't worry about the computations right now. We'll come to it in a later lab and you can do this, but we'll show you the logic. The question can be approached by treating the cell membrane as a capacitor in which the intracellular cytoplasm and the extracellular hemolymph are the conducting electrolytes. So the cell membrane itself is an insulator. Cell membrane is an insulating dielectric. So the external hemolymph, external extracellular fluid is this plate. So it's a liquid plate. And this internal plate we have is cytoplasmic fluid. So the capacitor plates are actually liquid plates in the case of neurons in our brain. Okay? The cell membrane itself is the insulating dielectric. A typical value for capacitance for a biological membrane is 1 microfarad per centimeter squared. So for a spherical cell with diameter 50 microns, that's typically the diameter of your neuron in our brain, the surface area can be calculated using these numbers, and then the capacitance can be calculated this way with the area added. Then what you do, if the cell membrane potential is minus 75 millivolts, the charge on the capacitor is given by Q is equal to V times C, if you recall from your high school physics. So if you calculate that, you get a charge of 5.9 into 10 to the power minus 12 coulombs. One potassium ion has a charge of 1.6 into 10 to the power minus 19 coulombs. So if you divide this number by this number, you will get the number of ions that need to make up this much charge that have moved down the concentration gradient. And that number turns out to be close to 38 million. Okay? So 37 million, let us say, ions leave to set up this concentration gradient of minus 75 millivolts largely. So does this alter the concentration gradient inside? Concentration inside? A cell with a diameter of 50 microns has a volume of this much. And if the potassium concentration is 400 micromolar, that means the cell has 1.04 into 10 to the power minus moles. So 1 mole consists of 6.032 into 10 to the power 23 ions. That is the Avogadro number, if you remember from your high school chemistry. And so the cell contains about 6.2 into 10 to the power 11 ions. That's huge. Thus, the loss of 38 million ions represents a concentration change of about 0.006%. So the answer is hardly at all. Note that the external volume is relatively huge, so the change externally is infinitesimal anyway here. By these ions coming there, it doesn't change. But this is a very, very surprising fact. Not surprising. This is something you need to know, that the 38 million ions leaving a cell to set up this membrane potential, that is 0.006%. So if you take a fraction, what is that? Add 2 more zeros, 0.00006 in a fraction sense of the total number of ions. That's hardly anything. So that's the point that these slides, we wanted to make with these slides. I think these slides were copied from a text where I believe I should give the reference here. I will correct it in later slides. Again, summary here. Origin of the resting membrane potential. I think I'd like you to read it. And I think that will be all as far as the second part of lecture of software experiment 0, dealing with Nernst and Rest potentials. If you have questions, please bring them to class. Otherwise, we will see you in class. Bye.